Okay, let's get started. We ready? Chapter 2. We're moving on. Chapter 2. All right. We got to review some algebra. All right. Now, some of you are going to go, oh my God, I can't believe we're going through this because you had this years ago. But trust me, there's some people around you in this room that are going to be very thankful that we're reviewing this. It's all about when you have equations. Matter of fact, I'm changing these to equal right now. Equal. Okay. You got to be able to take those equations and say, hey, what would x1 and x2, which are two different variables? Yes, they're both x. But because of that 1 and that 2, that makes them two different variables, just like if this were x or y or z. x1 and x2, where would they cross if these were lines on a graph? And by using one of these methods, I'm going to quickly go through all three of these review methods, hoping that one of them reach out and grab you. And whichever one, substitution, addition, or subtraction method, you find more comfortable for you, write a bunch of notes on that one, because you only need to learn one of these, whichever one reaches out and grabs you a little bit. But you got to learn one of them. Somehow or another, you're working on linear programming, you find these two equations to be the most important of all the equations. And you want to figure out where these two would cross if they would happen to be on a graph. So in order to do that, you need to eliminate one of the variables by doing one of these. And when you eliminate one of the variables, it makes it easy then to solve for the other variable. Then once you solve one variable, you plug it in, and you can solve the other one. Ready? I'm going to start with the addition method. If I add x1 and x1 straight down here, I'm going to add all the like terms. If I add 2 plus another x1, I'd have 3x1. So x1s would still exist. They wouldn't be eliminated. If I add 3 of them here and one of x2 here, my x2s, I'd have 4. Not eliminated. And this doesn't matter. I got to figure out, I'm going to have to change one of these equations so that I purposely will be eliminating one of the variables when I add them. So I say to myself, this would be easy to change because they're both 1s right now. What would I subtract from 2 to get rid of x1, and that would be negative 2. Or add, I'm sorry. 2 plus negative 2 would give me a 0. But how would I turn this into negative 2? Well, if I multiplied it by negative 2, it would be negative 2. Now, here's the key. If you multiply this by negative 2, you must change the whole equation that's involved. Or you're changing the whole thing. So when I decide that I'm going to multiply this by negative 2 so that when I add them, x1's gone, I have to multiply this by negative 2 and this by negative 2 also in order to have really the same line there. So, negative 2, I'm going to put an arrow here. Ready? Negative 2 times 1x is negative 2x1. Negative 2 times 1x2 is minus, come on, where'd this come from? Wow, different. What did I say? Minus 2x2, right? Negative 2 times positive 1. Negative 2 times positive 8, negative 16. This one's gone. Now I'm going to add the equations. I purposely set this one up to eliminate the x1. 2x1 plus a negative 2x1, x1's gone. 3x2 plus a negative 2x2 leaves me with just 1x2. 19 plus a negative 16 leaves me with 3. Is that right? Yes. x2 equals 3. That was almost too easy. Usually it takes a little more math than that. Now that I know that x2 is 3, I can plug it back into either one of these original equations and solve for x1. 3 will go into this one. So now I have x1 plus 3 equals 8. I subtract 3 on both sides. x1 equals 5. If I would have chose the other one, I would have gotten the same answer. Right? Everybody hear me? 3 goes into the other one. 3 times 3 is 9. Subtract 9 on both sides. You get 10. 10 divided by 2 is 5. No matter which one I plugged it into, because I did the addition method, I would have gotten the same answer. So, where's my answer here? Yeah, that is sloppy. Oh, there it is. There and there. 3, 5. Or 5, 3. I'm going to do this again using the subtraction method. Let's do substitution method. I'm going to get the same answer, 3, 5, no matter which method I use. It's just whichever one you feel most comfortable with, because there's a lot of people in here that math's not their thing. Okay, doing this again. You ready? Substitution method says, hang on, let me get this out of here. There. It says take one of the equations, isolate one of the variables to the left side of the equality, and everything else is to the right side, then plug it into the other equation for the variable you left by itself on the left. It looks like it'd be easiest to do this one, again, put an arrow here. I'm going to try to get x1 all by itself on the left, or x2, it doesn't matter, I'm going to use x1. So in order to do that, I got to subtract x2 on both sides, because whatever you do to one side, you got to do to the other, but that will allow me to get x1 all by itself. I end up with x1 equals 8 minus x2. It's all by itself. And I used that equation. So I jump to the other equation and plug that in for x1. This right here has to go in right there and do the math on it. This is 2 times whatever x1 equals, 8 minus x2. There's that for x1. Then I do the rest of the equation, plus 3x2 equals 19. All I have are x2's now, and I can solve for x2 by using algebra. 2 times 8 is 16. 2 times negative x2 is negative 2x2 plus 3x2 equals 19. I'm going to do two things at the same time. Subtract 16 on both sides and put like terms together. Negative 2x2 and a positive 3x2 leaves me with it 1 positive x2, right? So x2 equals 19 minus 16. The same thing, 3. Plug 3 in back to either equation, and x1 will be 5. Okay, that was the addition method and the substitution method, right? The subtraction method, which is almost exactly like the addition method, but you're trying to eliminate a variable by subtracting instead of adding this time. Ready? Get back here. Stuff's boring. So if I were to subtract without making any changes, I'd have 2x1 minus an x1 leaves me with x1. It's now eliminated. 3x2 minus an x2 leaves me with 2x2. It's now eliminated. I'm going to have to change one of the equations again so that I purposely am setting it up so when I subtract the two equations, one of the variables turns out to be 0. So I don't know what to do here. I'm going to try this one now. I say, let me turn this x2 into something so that when I subtract it from 3x2 in this equation, I get 0, which means when I subtract this, I need this to be a 3x2, so it turns to 0. So I'm going to multiply the whole thing by 3, purposely, so that when I subtract, I'm eliminating one of these variables. 3, but even though I only want to change that, if you change one part of the equation, you must change the whole equation. So 3 times x1 is 3x1. 3 times x2, positive 3x2. And 3 times 8, 24. All right. Now I am subtracting these two equations. 2x1 minus 3x1 is negative x1. 3x2 minus 3x2, 0. Gone. 19 minus 24 is negative 5. Is that correct?
Yes.
Divide both sides or multiply both sides by negative 1. x1 equals 5. The exact same answer we got when we used the addition method and when we used the substitution method. And now you plug in 5 into either equation and you'll see that x2 equals 3. All right. So at this point, you're saying to yourself, I want you to say to yourself, which one reached out and looked the easiest to you, and write some extra notes or whatever you got to do, because this is in your future. We're doing one of these. It's your choice which one you want to do, but you're going to have a couple equations in your future where I'm going to say, use one of the 3 methods to show me where these two equations would cross if they were correct. And I need to see you can do this. Excuse me. Now, this is all leading up. Oh, forgot. One more thing to review. How to graph an equation. A lot of people, it's been many years since they've had to graph an equation. And I want to review it real quick. You ready? What I always suggest is, what? I gotta remember here. Is by, what? I can't remember. Oh yeah, I almost forgot. It's where it would cross the axis is the best way to graph these, and then connect the dots. To do that is by putting in a 0 for one variable, we'll call this one x1, and then put a 0 in. Okay, this is kind of like this. And then put a 0 in for x2 and solve using, whatever equation you want to graph. Let's talk about graphing this one. I'm going to put a 0 in for x1 and see what x2 turns out to be. And that will tell me where it's crossing. We're going to make this our x2 axis, and this is our x1 axis. Now it will tell me where it's crossing. Yeah. I got it more than this. That's all right. They look semi-even, I hope. 0, 0. All that's left now is 0 times 2 is 0. So all that's left is 3x squared, or 3x2 equals 19. 3x2 equals 19. I divide both sides by 3. Help me out. 19 divided by 3. Alexa. What? 6 1/3. Thank you. 6.33333. And now I'm going to graph that. x1 at 0, x2 at 6.333, x1 at 0, 1, 2, 3, 4, 5, 6.333. Now I'm going to put a 0 in for x2 and solve for x1. 0 times 3 is 0, that's gone. I get 2x1 equals 19. I divide both sides by 2. I get 7.5, 8.5? 9.5. That's what I meant. 9.5. And I put a dot at x1 is 9.5, x2 is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9.5. And then I take a straight edge. Hang on. Boy, darn, that was close. Add my little arrows, continuing. Now look, see this graph? We got quadrants here. You will never have answer here. Always in this quadrant is your answer. Sometimes the lines are down here. You must extend those lines into this quadrant because this is where your solution is going to be. Now, if you got one that has a dot down here and a dot here, you need to connect them and extend it out into here. This is where your answer is going to be. All right? How are we doing? You ready? So, we have a story problem. There's a limitation of 6, limitation 19, 8, whatever they represent. We're told, you think this is profit or cost? Because of the max, probably $5 and $7. We don't have the story, but just are given the objective function constraints, but we're pretending hypothetically this is a story. And now you're asked to solve it using the graphing method. You then start graphing every one of these constraints using this method where you put a 0 in and find where it crosses the axis. Now some of these, they only have one variable. So you just got to say, it's pretty much like, if I were to make x1 6, because it says x1, I usually turn them into equal. It makes it a lot easier. Forget the less than or greater than until you get to shading. This is what's coming up. So I make them equal to draw the line. It says x1 equals 6. Well, how do you graph that? You just go, well, if x1's 6, what would x2 be? And the answer is, it can be anything as long as x1 equals 6. I usually throw in like any numbers right in a row like that. 6, 1. Well, 1, 2, 3, 4, 5, 6. No. Yeah. 6, 0. 6, 1. 6, 2. And you start to get the idea. Okay, it's a straight line up and down. And it looks like this. 6, 0, 6, 1, 6, 2, 6, 3. And there's one variable, and you make it an equal sign, whether it's less than or greater than, get rid of that. You'll go, oh, this variable has to be 6. You can make the other variable anything to create the line. Now, which way to shade? Let's go back to the original equation. That's where either the less than or the greater than comes into play. This is the easiest way. I don't even remember what it says on the PowerPoint, but I'm going to show you the easiest way to determine which way to shade. You pick any dot on either side of the line you just grabbed, and you see if it makes sense. That's the easiest way. Okay, I love picking 1, 1. Those are always my easiest. Let's see, 1, 1. I picked a dot. It's on the left side of the line. If this makes sense, then my shading goes this direction. If it doesn't make sense, my shading goes that direction. So by testing one point on either side of the line, you can determine whether you're shading that way or the opposite way. You don't need to do anything else. You don't need to do another point. So 1, 1. Well, there's no x2 to put a 1 in, but there's x1. So if I put a 1 in for x1, is it less than or equal to 6? Yes, it makes sense. The shading goes that way. What if I would have picked 2, 2? I put a 2 in for x1, x2 is not even part of it. Is 2 less than or equal to 6? Yes. Proves the shading goes that way. You get it? What if the person next to you picked, again, 7, 1? Great. Go back here, plug it in. There is no x2, plug in the 7. Is 7 less than or equal to 6? No. Don't shade that way. It must be the opposite. Got it? All right. Next one. I think we just did this one, right? Is that this? We plug in 0 for x1, we get 6.3. We plug in 0 for x2, we get 9.5. Let's make sure. 0, 6.3, 9.5, 0. We put those dots on the graph, we connect them. We pick a point on either side. I love 1, 1. It's my favorite point because it's so easy. Let me go back to the original. Put a 1 in here, put a 1 in there, and see if it makes sense. That would tell us that's the way the shading goes. 1 times 2 is 2. 1 times 3 is 3. 2 plus 3 is 5. Is 5 less than or equal to 19? Yes. That's the direction to shade. So you'll see all the shading going this way. Now, this is being done on one graph. And so you have all this shading starting to overlap each other in some areas and not overlapping in other areas. So when you're doing this, and you're going to have one of these on the test that you may have to do a little shading, don't make your shading so dark, because this is all leading to where you have to determine where all the shades overlap. Let me repeat that. Not just where 2 shades overlap or 3. However many constraints there are, all the shadings must overlap. And that's the area you're looking to pick on. Everybody hear that? You're looking for the area where every shade overlaps each other. Not just part of them overlap, all overlap. Darn it. Doesn't show it with all 3 of them before we get there. If it showed all 3, you have a whole bunch of shading going this way, shading going this way, and then more shading going this way. But this is the only area where all 3 shadings overlap. This little area right here only had 2 of the shadings overlap, not all 3. So that's where most mistakes are made, right there. It's where every shade overlaps. We'll talk about the third equation we skipped. x1 plus x2 less than or equal to 8. You plug a 0 in for x1, x2 is 8. Plug a 0 in for x2, x1 is 8. 0, 8, 8, 0. You go to the graph, you put a dot at 0, 8. You put a dot at 8, 0. Connect the dots. Pick a point on either side. My favorite's 1, 1. I go back up here and plug 1, 1 in. 1 plus 1 is less than or equal to 8. That's the direction I'm shading in. Right? Too easy? It's easy as I'm describing it to you. But if this is not your thing, I'm telling you, 2 or 3 days from now, this will look like a foreign language. It's just really hard to, unless you've done a bunch of them, it's really hard to remember it. So write some good notes. We got all our shading done, and now it's all about figuring out where the shades overlap. On this problem, for your next quiz, you have a question that says, identify the feasible region. In the feasible region, you need to put some dark lines to show me exactly where you believe the feasible region is, where you believe all the shades overlap. And someone's going to put this all the way to here and down. And then they're not going to put that line across there. That's why I make it really dark so I can see what you are determining is the feasible region. Matter of fact, some people even darken up the shading to make sure it's obvious what you are showing me. Some people will put feasible region with an arrow right there and make that line really dark. But it's got to be obvious. To say, show me the feasible region. It's where all the shades overlap.
Can we highlight it?
Highlight is great. I'll take it any way you want. As long as it's obvious to you and not it'll be obvious to me. Okay? Now, you ready? How many points are touching the feasible region where there are two lines crossing of any kind? You want me to repeat that? Yeah. You ready? Look at this graph. You're looking to tell me how many points, how many spots you see two lines crossing where it's touching the edge of the feasible region. How many? 5. 5. Who said 2? That's all right. You don't want to identify yourself. I'm not trying to embarrass you because at first glance, usually it's 2 or 3. But there's 5. Because you got to remember 0, 0 is where two lines are crossing and it's touching that feasible region. And then right here, you got these two little ones right here that sometimes people will think is only 1. But you got right there and right there. So here's 5. Right there, crossing the x1 axis. 0, 0, where it crosses the x2 axis. And then these two little ones where we have some of the constraints cross each other, but they're also touching the feasible region. The 5 points you just saw are called the extreme points. And one of those extreme points are your optimal solution. Did you hear that? That's where your optimal solution lies. When you get all the constraints graphed, and you find where all the shades overlap, all of these points in here are meeting the requirements of those limitations. But that doesn't mean they are your optimal solution. Your optimal solution is always one of the extreme points that are touching the feasible region where there happens to be two lines crossed. Now, in the old days, many years ago, before personal computers, which is when I had to do all this, before personal computers, we would use either the subtraction method, the addition method, or the substitution method to find every one of these points. Now, this would be easy, and even this one, because we did already figure out what this point is in order to put that dot there. And this one's easy, but it's these two where you, if you try to eyeball it, even though it looks obvious to you, you're making a huge mistake. That in real life, that point, even though it looks like it's exactly, what is that, well, you know it's 6 bars. You know, maybe you think it's 2. In real life, that won't be 2. That you have to figure out by using what two equations are crossing right there, forming that point, and then you take those two equations and you apply either the substitution, addition, or subtraction method to find out exactly what that point is. Same with that one right there. Then you can take every one of these 5 points and plug them into the objective function, and the one that meets this requirement is your optimal solution. That's the long way to solve it. Now I'm going to teach you the shortcut. Right? But you're more than welcome to use either way. Okay. The shortcut, some people hate the shortcut, but you have to graph the objective function even though the objective function is not equal to anything. So, in order to graph the objective function, this is the part everybody hates. You ready? I want to make sure everybody's attention and the camera's rolling. All right. To graph the objective function, you must make it equal to some arbitrary number you pick out of the air, and everybody here can pick a different number. It doesn't matter. And when you go to take the quiz, you're going to say, what number am I supposed to use to graph this objective function? Because you're going to forget I said any number you pick. You can pick 5, 10, 100, 2,000, any number. Make the objective function equal to that number and graph it the exact same way you graph any of these other ones. Make one of the variables 0, solve, make the other variable 0 and solve, put the 2 dots on the axis and connect them. But you got to make it equal to a number. Now, my suggestion, make it equal to a number that makes it easy on you. Make it equal to a number maybe that both 5 and 7 or whatever numbers are here go into evenly. I usually say, oh, what's 5 times 7? Let's make it equal to 35. That's pretty easy. Or 70. You know, something that you know both numbers go into easily makes it easy for you. But you can make it any number you want. You could, you know, just like we got 6.3 here and 9.5, if you make it some odd number, you'll get odd numbers like this. But here's what's going to happen. You pick one number, the person next to you picks another number, you're all going to have lines that are exactly parallel to each other no matter which number you pick. Some of your lines are going to be here, some here, some here, some here. Whichever number you pick, you're going to have a line, and they're all going to be parallel to each other if you're doing it correctly. You're just picking different spots where that line's going to land on your graph. And wherever you decide, whatever number, if you use 35 like I would have, 39, 42. Now that, no, 5 doesn't go into 42 evenly. 70, whatever number you pick, and you finally get your line on there, you now got to take that line and say, if this line were entering or leaving the feasible region, where's the very last little spot it would be touching the feasible region if it's almost out of it. So, if your line's out here coming in, where's the very first spot it would touch this feasible region? If your line's down here heading out, where's the very last spot it would touch? And if you did this right, either that spot, whether you're coming one direction or the other, is going to be an extreme point. And it happens to be the extreme point that is the optimal solution. And then you only got to do the substitution, subtraction, or addition method on just the one point that you discovered by graphing your objective function. I used to only graph my objective function once. And then I'd grab a straight edge. This is always hard because this is such a big screen. And then I'd grab a straight edge, and I'd start just staying parallel, moving my straight edge out or in to figure out where it would touch last without having to do a bunch of math to draw all these lines. I just drew it once and then use a straight edge from there. So I can see, I know this is a max problem, so I know 0, 0. There's no way that could be the optimal solution. And I know the numbers have got to be one of these other ones out here. So because my line is in here, I'm moving outward. But if my line would have been out here, I would have been moving towards it, just to find out. I know now the optimal solution is one of these 4. Look at how this line's already past this, so that can't be the optimal solution. I got it down to 3. It's either right here, or right here. I just want to refresh your memory. These are the extreme points. That's where these points came from. We know now the optimal solution is one of these 3, because all our objective function lines, as we move parallel, have passed these 2. Right? Wait. You see that one already? Darn. Shoot. All right, look what's happening here. If we had a straight edge and we kept going out like this, I think we would end up passing this one. You agree? Now it's down to these 2. And I don't have a straight edge big enough. But if I did, and I start heading out, and I'm truly parallel, you would end up seeing that it passes that one, and the very last one it would touch is that one right there, which is the next slide that I tried to avoid. And that is your optimal solution. Now, right, this is your optimal point, your optimal solution. And you got to say, you go back to your graph, and you go, which lines are forming that point? Let me go back right here. Which lines are forming that point? You follow this line, you go, oh, this is this equation, and you go, that equation. These 2 equations that we started this whole lecture with are the 2 equations that are forming the optimal solution right there. You use the objective function to find which extreme point out of the 5 is the optimal solution. You're going to now apply one time. You don't have to do it 5 times. One time, the substitution method, addition method, or subtraction method. And every time we did it, no matter which way we did it, we got, we don't have the answer up here, was 3 and 5, wasn't it? Where is the answer? Was it 3 and 5? Yes. 5 was x1 and 3 was x2. And sure enough, that point right there is 5, 3. We found the optimal solution. Crazy? This is too much, isn't it? Can you believe it? What the heck do we have in this algebra? We got computers. What is going on? All right, hang on. You ready? Where am I? Boom, posted on Blackboard. x1 less than equal to 6. 2x1 plus 3x2 less than equal to 19. x1 plus x2 less than equal to 8. Does this look familiar? Our objective function numbers, 5 is with the x1, 7 is with the x2. I posted this so you can reuse it and reuse it when there happens to be two variables. You add columns as there's more variables, or you grab the other one I posted, which is the exact same one. I've added columns for additional variables, which is where we're heading. This is the same one, I'm only using these two columns because the problem we're solving only has two variables. I'm ignoring these three columns. I'm not using them. But I know there's problems in the future where we'll need that column and that column and that column, and you need to get ready to add more columns. And in real life, I had problems where you had 25 variables and 100 constraints. So you're not solving this off the top of your head. Just going, oh, that's got to be, there's no way. Now, right here is where your optimal solution is going to arrive. These have to start at 0 so Excel can find your optimal solution for you. If we do this right, this should turn out to be a 5 and this should be a 3, correct? Here is your objective function formula, which is 5 times x1 plus 7 times x2 max. I have to use cell locations here. You do too. And they're already there for you when I posted this. So before we even look at this, I want you to think about what would be here using cell locations. Equals, I gotta look again. I didn't know we couldn't see it. Man. We can't get it. What do I gotta do here? Go there? There we go. Do we see it now? Right here is going to be E10 times E10 times whatever the optimal solution is going to be for x1, which is E14. So E10 times E14 plus F10 times F14. Now, where did I get that from? Well, I'll make sure you understand. I can tell I'm losing a couple people. You ready? I'm trying to recreate this. 5 times whatever x1 is supposed to be, plus 7 times whatever x2 is supposed to be. And that's what I'm putting in that objective function, whether it's a max or a min or whatever it may be. I'm trying to recreate that using cell locations. Now, we're looking at this one. So right here, E10 times E14 plus F10 times F14. Here is the left-hand side of each constraint, 6, 19, and 8. Less than equal, less than equal. This is here for visual effects only. You don't have to insert these. I just do that because I like to remember if it's a less than or greater than or equal. Here is cell locations that I'm not showing you right now because I want to show you how it came about. It'd be just like the objective function, or just like the constraints written on the left side, but the cell locations for these variables are where the optimal solution is going to be for those variables. So right here is going to be, no, let's go to the second one down, right here. It's going to be this cell location, E8 times E14, which is this one, E8 times E14, plus F8 times F14. That's exactly what's in that second one down, right there, E8 times E14 plus F8 times F14. The dollar signs. The dollar signs is because when I write this equation and I copy and paste it down, I don't want these cell locations to change. I want it to always be at E14 and F14 because this is where the optimal solution is for this, 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 and this. Those same exact two cell locations. Can somebody tell me what would be right here, cell locations? Anybody want to grab this? What would this be? E what? E what, 14? I didn't hear you. E14 times what? E8. No, E9. E9 plus Not point the third one down. Plus, come on, someone. F9. That's right. Times F14. This times this. Sure enough. E9 times E14, F9 times F14. Now, on the Excel spreadsheet, I'm giving you the page number from your book. Can someone confirm it? Because this is an old spreadsheet, and I don't know if it's still page 89, whichever edition you have. But if it's the, what is this, 14th edition, I think it's page 89. And the instructions say, first of all, this computer I just got late last year, so I didn't have something on there, and I had to add it. And when I had to add it, I had to go to File, go right down here to Options, and right here where it says Add-ins, you don't have, I can't remember the name, but I'm about to show you though. Add-ins right there. Am I on add-ins? There we go. And then where it says Excel add-ins, you hit Go. And you want to add the Analyst tool and the Solver add-in. These two. You click OK and give Excel a second. It takes a second to install. You'll have these little tools. You're going to have canceling because I already installed it. And it'll all of a sudden be under your Data tab. Data, and right there's Data Analysis and there's Solver. They'll show up after you do that add. I'm going to click on Solver, just like page 89. Where is it? Is it on page 89? Yeah. Solving linear programming using Excel Solver. Page 89, I don't know what page on an earlier edition. You ready? Solver. The first word, set objective, put this in your notes. Set objective is the cell location where the objective function formula is. The set objective is the cell location where the objective function formula is. So, in this one, it's right there, E16. That's where the objective function formula is. So I'm saying set objective E16. Next it says max or min or value up is the max. Then it says by changing variable cells. This is where you tell Excel where your optimal solutions to be placed. Right here, what is this? E14 and F14. If you had more variables, it'd be more. E14 and F14. So I'm going to put E14 colon F14. So I'm telling it from E14 to F14. Thing. I don't think I have to equal. You know what? I'm going to do it this way. I'm just going to highlight these two. There it is, E14, F14. It just added the dollar signs, used uppercase letters. Now, here's the hard one. Subject to constraints. This one, to add a constraint, so that we have 3 of them, so we got to do this 3 times. We're going to click on Add. This little box pops up, and it's asking you, where is the left-hand side formula for that constraint? Which is one of these 3. We'll do the first constraint. The cell location where the left-hand side formula is right there at E20. Then you go to the middle, and there's a down, you get a pull down, and you select, is this a less than equal or greater than equal or an equal? In this case, we're going to go with the less than equal. Okay, and then, this is asking where's the right side of the constraint, which is right here. And this one's the first constraint, so I'm just going to click on this cell location right here, J20. Now you click OK, and this says E20 less than equal to J20 is your first constraint. I want to add another constraint. Here we go a little faster. Add. Second constraint, where's the cell reference? Be the second constraint down, which is E22, 21. This is also less than equal, so I'll leave it at less than equal. The right-hand side, right there at J21. And I'm going to skip looking at it. I'm just going to add another by clicking right here. I'm adding another. This one's going to be E22 less than equal to J22. Now click OK. All three of them are there. E20, E21, E22, J20, 21, 22, less than equal, right? All right, you write good notes because you must click this box that says makes unconstrained variables non-negative. Remember I said all semester our variables are always going to be 0 or higher. We'll never have negative numbers in our variables. This is when you click this, is what you're telling you. So you don't have to do those constraints, less than equal to 0 or greater than equal to 0. And then the method, there's nonlinear and all this. You must pick simplex linear programming, the simplex method. In my day, we had to manually do the simplex, which is like a stepping stone method. And then you hit solve. It's going to happen really fast, and the thing pops up and says, is this okay? And you click OK. This is where all the solution is going to be. You're going to see the numbers change really fast. You ready? Hit solve. What should we get? 5 for x1 and 3 for x2, correct? That covered it up. 5 for. All right, we just used Excel to solve it. And we have just enough time to now use the software to solve it. You ready? And then we're out of here, and we have the rest of the week off. Is that correct? We should head to the bar. I don't drink anymore. All right. Doesn't mean we can't have pizza. Hang on a minute. I gotta find. Okay, I'm gonna open up a new one. I already did it. Nobody's bringing me thumb drives, but if you want this software on your home computer, just bring me a flash drive and I'll put it on there. I can't email. It's way too large. Kind of. And it never makes it through the server at your time. You can't email software. Just pay for it. Just get it from me. So it's so old I can't imagine it's still for sale. Okay. Oh, I didn't want to do that. Hang on a minute. Let me get to the main menu here. Change modules. When you first open up the software, it looks like this. It's asking you which one you're doing. Right now, we're at module 1, which is linear programming, okay? And then you click linear programming, and it says, you go up to File, and it says, do you want to open one you've done already, or a new one? We're doing a new one. Now you answer these questions. How many decision variables were there on that first example? 2, x1 and x2. How many constraints were there on that first example? 3. And then is this a max or a min? Max. When I open this, it will put however many variables you say, it will always make it x1, x2, x3, x4, however many you told it. You can change those variable names to whatever you have on your piece of paper or whatever you're looking at if it makes it easier for you. It's just this easy. You just click right there and you go, how about x? And let's change this one to y. And as soon as I click out of there, it changes them below automatically. But actually, we are using x1. We are using x2. I just want to show you how you change it. Up here at the top is whatever numbers are with the variables in the objective function. What's with x1 when you read the objective function? I don't even remember.
5.
Is it a 5? What's the other one then?
7.
5 and 7? Okay. 5 with x1, 7 with x2. Let's go down here to the 3 constraints. Does the first constraint happen to have a number with x1, or is even x1 in the first constraint? Everybody remember the first constraint? Yeah. x1 less than equal to 6. x1 is there. Is there a number with x1? No. So what number would you use? 1. Because there is an x1. What numbers with x is x2 in the first constraint? No. So there's no number with it. So what do we put here?
0.
Or?
Leave it blank.
Or leave it blank. 0 or leave it blank mean the same thing. It doesn't exist. I'm going to use a 0. Right here, you do not have to put the equals with the less than or greater than, because there's always an equal involved with every constraint. It's either less than equal, greater than equal, or equal for this whole semester. All you got to put is the less than, the greater than, or the equal. In this case, it's less than equal, so I'm just putting the less than, which means less than equal. The right-hand side is a 6, is that correct? 6. Now I'm going to go a little faster. Somebody looking at the constraints, what number? The second constraint right here, 2, 3, and 19, is that correct? Yes. 2, 3, less than 19. Quick warning, I would put in your notes. Never use the enter return key on this, or you have to start all over. Use the arrows. As soon as I hit enter or return key, this says undefined something something, and you can't get back and keep working. You've got to start all over. And you'll just waste a bunch of time. I've learned the hard way. This one's x1, x2 less than equal to 8, is that right?
Yeah.
So 1x1, 1x2 less than 8. If I did this correctly, we should see that the optimal solution is x1's 5 and x2's 3, correct? You ready? File, oh no, solution, solve. The optimal solution on these outputs are right at the top here. The value for x1 is a 5, x2 is a 3. There's your optimal solution. And as we finish this chapter, I'm going to teach you what all the rest of this is. That it's all on the graph also. A lot of this is on the graph, which we're going to talk about. I guess next week, is that true? I'm showing up Thursday just in case.
I'll look at the website.
It just doesn't make sense. How can we not have that? I didn't read this. You guys tell me. Is this for sure?
Yes.
Wow. So you'll have no homework this weekend? Hunter wants it early. But I change the homework every semester. All right, I'll see you guys next week, I guess. Unless there's some mistake, I'll see you Thursday. Yeah, let me grab this.